Don't get too excited. This is joint work with Nicolas Trognon, Théophile Trang, and Christina Vushkovich. All right. Let's see. No? Okay. Okay, thank you. All right, so the first few slides will be sort of an introduction to people who have never seen perfect graphs, and then we'll launch into the complicated details. All right. So you know what a graph is. A graph has vertices and edges, and then I want to think about the chromatic number of a graph. So that's coloring a graph for me means assigning colors to the vertices so that if two vertices are adjacent, they get different colors. And then the chromatic number is the smallest number of colors you need in order to be able to color your graph in this way. And then there is kind of a companion parameter, the clique number. So that's the biggest size of a clique in my graph. And what that means is, so a clique is a set of vertices all pairwise adjacent. And then, so an obvious inequality is the chromatic number is at least the clique number, right? Because if I have a clique of size k, I need to color all its vertices in different colors, so I need at least k colors. Okay. So, all right, so there's an obvious inequality in one direction, and now you might ask when is there equality? And it turns out actually equality holds in quite a few interesting cases, sort of many natural classes of graphs you can think about. You can think of equality holds for them. So, for example, bipartite graphs or complements of bipartite graphs, right? So a complement of a bipartite graph is just two cliques with some edges between them. And it's not hard to see that the clique number and the chromatic number are the same comparability graphs. So that's when you take a poset, a partially ordered set, and you make a graph whose vertices are the elements of the partially ordered set, and then you make two elements adjacent. You make two vertices adjacent if the two corresponding elements are comparable. So that's also not very hard that the comparability graphs have this property. All right, so then one might think maybe this question has a nice answer. When is the chromatic number and the clique number the same? But it turns out you can cheat. So you can take not a very big graph, and then you can take disjoint union with a huge clique. Right? So for example, here, a clique on at most 99 vertices, some general graph on at most 99 vertices, and then disjoint union with a clique of size 100. All right, so here, of course, the clique number and the chromatic number are the same, just because there's this huge clique sitting there in a separate connected component, right? So you're allowed to use 100 colors, and you can also color every vertex here in a different color. But somehow this is not a satisfactory answer, because all the action is here, and I didn't learn anything about that part. All right, so that means this is not quite the right question yet. But there is a right question which is not far. And this question was asked by Claude Berge in roughly 1960, 1961. So he said, let's ask for which graphs the following is true. The chromatic number and the clique number are the same, not just for the graph I'm looking at, but also for every induced subgraph. So let me tell you what an induced subgraph of a graph is. So you know probably you know what subgraphs are. You take a graph, to get a subgraph, you're allowed to delete vertices, you're allowed to delete edges. And for an induced subgraph, you're allowed to delete vertices, and then if you delete the vertex, you have to delete all the edges incident with it, but you're not allowed to delete any other edges, right? If I decided not to delete this end of this edge and this end of this edge, then I have to keep the edge. So this is how you say it formally. All right, so let's do an example. So I start with this graph, then this is an induced subgraph of that, because to get this from that, all I do is delete this vertex, and the edge is instant with it. This is not an induced subgraph of that. The easiest way to see it is they have the same number of vertices and different number of edges, right? And I'm not allowed to delete edges without deleting vertices. Okay, so once again, now that we learned what an induced subgraph is. A graph is perfect if the clique number and the chromatic number are the same for every induced subgraph. All right. And so Claude Berge defined these perfect graphs, and then he made two conjectures about them that became quite famous and generated a lot of work. And so they've both been solved by now. The first one is the weak perfect graph conjecture that says a graph is perfect if and only if its complement is perfect. So it was a conjecture of Berge, and then now it's a theorem of Loas. Maybe I should tell you what complements are. So if you take a graph, its complement is the graph whereas the adjacencies are exactly the opposite, right? So I start with this graph, its complement has the same vertex set, and two vertices are adjacent in the complement if and only if they're non-adjacent in the graph. I'll say this again later when it's a little bit more important to us. But so there was that. Then there was a strong perfect graph theorem. The strong perfect graph conjecture that's now the strong perfect graph theorem. And so what that says is that a graph is perfect if and only if certain induced subgraphs are not present. So what induced subgraphs? Cycles of odd lengths at least 5 and complements of cycles of odd lengths at least 5. All right? Now, if you believe this, you should believe the top theorem, because here you see explicitly that everything is preserved and taken complements, right? The induced subgraphs I'm forbidding are a family and its complement. So if you believe this, you should believe that. But chronologically, they were proven in the opposite order. All right, and then there is another theorem about sort of another natural question about perfect graphs, which is also now a theorem. If I give you a graph, can you test in polynomial time if it's perfect? So the answer is yes, and it's a theorem with Kornjels, Liu, Seymour, Bushkovich, and me. And I think it's 2005. I'm not actually sure. Yes.
So she want to know the example for the first theorem, when G is perfect and G complement.
So what does she want? An example?
And G is perfect, G complement, you said?
So, for example, bipartite graphs are perfect and complements of bipartite graphs are perfect. I'm not sure. Okay. All right. All right. So this is not sort of crucial to what we're doing. I just want to say something about perfect graphs. You know, people work on perfect graphs. Perfect graphs are interesting. Okay. So. Right, so another sort of natural question was, if I give you a graph, is there a polynomial time algorithm to test whether it's perfect? And the answer is yes. So that's a theorem from a few years ago. The complexity is quite high. It's n to the 9th. If I give you a graph with n vertices, it takes time n to the 9th to check if it's perfect. But the algorithm has two bottlenecks. So there are two separate steps that take n to the 9th. You'll have to work hard to improve it. Anyway, so this is sort of a general overview. And now we get to something that's more relevant. There is still a big open question about perfect graphs. How do you color them? Is there a combinatorial algorithm that, given a perfect graph, outputs an optimal coloring, right? So there is a polynomial time algorithm, but that uses the ellipsoid method. So the question sort of is not completely open, but what about the polynomial time? I'm sorry, what about a combinatorial algorithm? You know, an algorithm that says delete this vertex, add that edge, you know, look at this subgraph, things like that. All right, so that's open, and that's possibly sort of the biggest open problem left in perfect graphs right now. And so I'm going to say something about that. All right. So first of all, there's a remark to make. If I want to color, if I want to color perfect graphs, or if I want to color a class of perfect graphs, it's actually enough to solve a different problem. It's enough to be able to find the clique number and the stability number. I should tell you what the stability number is. So a stable set is the complement of a clique. It's a set of vertices where no two are adjacent. And then if I give you a class of perfect graphs and I want to be able to color every graph in this class, it's enough to be able to find the clique number and the stability number of every graph in this class. Right, so the stability number is the size of the biggest stable set. Now, what I said is almost true as you can see here. So what I need is, I need to be able to find weighted cliques and weighted stable set. What that means is, so I have a graph, and now I'm going to have numbers on the vertices. I'm going to have weights on the vertices. And in order to be able to color, what I need to find is the weight. So I need to find the weight of the heaviest clique, right? Not just a clique that has as many vertices as possible, but a clique that has weight as big as possible. And also I need to be able to find weighted stability number, which is the biggest weight of a stable set. All right, so we're interested in coloring, but really, I should say, so this is the theorem of Kritochvil and Sebo and Trotnion and Vushkovich. So Kritochvil and Sebo did it earlier, but Trotnion and Vushkovich have a one-page proof that I can understand. So I thought I would quote them both. Now, so we're interested in coloring, and so immediately we say, forget coloring, let's just concentrate on this problem. Let's concentrate on the problem of finding weighted, maximum weighted clique and maximum weighted clique number and maximum weighted stability number. And then another remark that would make our lives easier is this. So if the class of graphs I'm looking at is actually closed under taking complements, then of course it's enough to find weighted clique number, right? Because stability number is clique number in the complement. So for example, if we were ambitious and we were trying to color all perfect graphs, that immediately reduces to finding max weighted clique in a perfect graph. Actually, in that case, you can make it even a little bit simpler. You can delete weighted, but let me not talk about that. All right, so with this in mind, let's keep going. So in order to prove the strong perfect graph theorem, the theorem that gives an induced subgraph a forbidden induced subgraph characterization for perfect graphs, what we did was, and so we in this context is Neil Robertson, Paul Seymour, Robin Thomas, and me. What we did was we proved a theorem that describes the structure of all graphs that don't have this induced subgraphs, and then we used it to prove that all such graphs are perfect. But now, so what you kind of can get out of it is a certain theorem about the structure of perfect graphs. So let me tell you what it says. It's a little threatening, but we're going to compress it. So it's going to look like that just for one slide. All right, so the theorem is that if I give you a perfect graph, then one of 6 outcomes hold for it. Well, it depends how you count, but so maybe your graph is perfect. Maybe your graph is bipartite. Maybe its complement is bipartite. That's the first outcome. Okay, let me give up on that. Maybe your graph is the line graph of a bipartite graph. If you take a bipartite graph and then you take its line graph, what you get is a perfect graph, and then maybe your graph is a complement of a line graph of a bipartite graph. Maybe let me tell you what these things mean. Here we go. So first of all, complement, let me say it again because now it's actually important. If I start with a graph, its complement is a graph with the same vertex set and an edge is in G complement if and only if, so a pair of vertices is an edge of G complement if and only if it's not an edge of G. And then line graphs is the following. So you start with a graph, and now you're going to construct a new graph that sort of records the intersection pattern of the edges of the graph you started with. So I start with G, and then I make a new graph called L of G. The vertices of L of G are the edges of G, and then 2 vertices of L of G are adjacent if and only if the corresponding edges share an end. Right? So I make sort of I say these 2 edges are adjacent if they share an end in the graph I started with. All right, so now you believe that. So let's go through these possibilities again. So maybe your graph is bipartite, maybe its complement is bipartite, maybe your graph is the line graph of a bipartite graph, maybe your graph is the complement of a line graph of a bipartite graph, maybe your graph is what's called a double split graph. It doesn't matter what it is. It's a class of graphs. You can describe them explicitly, but it doesn't really matter. And then there are 3 other outcomes which are sort of, in some sense, less nice, and they just tell you, they don't tell you explicitly that your graph belongs to a certain family, but they tell you that your graph has a certain structure. So the first outcome is that the graph admits what's called a balanced skew partition. Let me show you what that is. Here we go. So it's the picture on top. That means you can partition the vertex set into 4 parts called A, B, C, and D, so that A plus B, A union B is a cut set. So there are no edges from C to D. All four parts are non-empty, and there are no edges from C to D. But also, C union D is a cut set in the complement, which means every vertex in A is adjacent to every vertex in B. And then being balanced in some condition about the length of path that start and end in A, and start and end in A union B, and have their interior in C union D, and a similar thing in the complement. So it may not say exactly what it is, but it's a technical condition. Right, so we're talking about this balanced skew partition. So I told you what a skew partition is. A balanced is some technical condition that I don't want to talk about right now, but all that matters to us is that it's invariant under taking complements. So if a graph admits a balanced skew partition, then so does its complement. All right, so the next possibility is that G, or the complement of G, admits a two-join. Let me tell you what that is. Yes? Okay, I guess we'll postpone the question. Okay, I understood that. Okay, so let me tell you what two joins are. Graph admits a two join if you can partition it into 2 parts, the top part and the bottom part, and the edges between top and bottom are somehow under control. So what does that mean? So the top has three disjoint parts, A1, C1, and B1, and the bottom has 3 disjoint parts, A2, C2, and B2. A1, everybody in A1 is adjacent to everybody in A2, everybody in B1 is adjacent to everybody in B2, and there are no other edges from top to bottom. All right, so that's what a two-join is. And then, so let me just tell you, for the future, I'll need to talk about something called even two joins and not two joins. And what that means is, let's think about the length of path from A1 to B1 contained completely in the top. I claim they all have lengths of the same parity. Why? Because, so let's take, suppose I had an even path like this and an odd path like that. So again, it's a path that starts in A1, ends in B1, and otherwise it's completely contained in C1. So suppose I had an even path like that and an odd path like that. Let me also take a path from A2 to B2 with interior in C2, right, so in this part. And you should ask why such a path exists. Well, that's one of the technical conditions of being a two-join. Such a path exists. Now, so this path has some parity, say it's even. But then I can complete it through an even path here, and I complete it through an odd path here. One of them gives me an odd hole. One of them gives me an induced odd cycle, right? So that means all paths here have the same parity. And that's what this refers to. So a two-join is even if all paths here are even, all paths from A1 to B1 with interior in C1 are even, and a two-join is odd if all such paths are odd. And so another small observation, if a two-join is odd, so I know that all these paths are odd, but also all those paths are odd. Because if I had an odd path like this and an even path like that, again you go odd, plus 1, plus even, plus 1, that's odd. Okay, so these are two joins. And now we're almost done with the theorem. There's another decomposition. The last outcome is that my graph admits a homogeneous pair. And so then later it turned out that actually you can do without this outcome. The theorem is true if you just omit homogeneous pairs altogether. That's my theorem. But I want to mention them because actually in what we are doing, we'll have to bring them back. So let me just tell you what a homogeneous pair is. Okay, here we go. So that's just the top picture. So that means you can you can partition the graph into this 6 sets, A, B, C, D, E, and F. And I'll say A and B is a homogeneous pair. What that means is that from the point of view of the rest of the graph, A and B sort of behave like single vertices. Every vertex outside of A union B, if it has a neighbor in A, it's adjacent to everybody in A. If it has a neighbor in B, it's adjacent to everybody in B. Right? So that's what this picture means. C are vertices that are adjacent to everybody in A, not adjacent to anybody in B. D are adjacent to everybody in B, not to anybody in A. E are adjacent to both, and F are not adjacent to both. And that's the whole graph. All right, so we'll come back to this slide in a minute. But this is a theorem. So either you're in one of these classes that are described in outcomes 1 through 3, or you admit one of these decompositions. And I'm going to call graphs that satisfy the first 3 outcomes basic. Right? So a perfect graph is basic if it's bipartite or complement bipartite or line graph of bipartite and so on. All right, so let's keep going. So now, skew partitions, I told you everything I wanted to tell you about. Let's think some more about two-joins. So if my graph has a two-join, I want to say I'm now going to break it apart into smaller graphs or into simpler graphs. And what that means is the following. So here I am. I started with a graph that admits a two-join. Oh, sorry, something bad happened to my picture. The little circle next to C1 should be around A1. Okay, I'm not sure what I did. All right, so now I'm going to break this graph into 2 parts. So the 2 parts are essentially going to be the top and the bottom, A1 plus C1 plus B1 and A2 plus C2 plus B2. Except I want to keep a little bit more information. I want to add a path like this, a path that keeps track of whether the two-join was odd or even. So I'll take the part that corresponds to A1, B1, C1, and then I'll add a vertex complete to A1, a vertex complete to B1, and a path between them, right? So this is sort of remembering a vertex from A2 and a vertex from B2. And this path is going to be, of the length of the path corresponds to the parity of the two-join. If it was an even two-join, I'll add an even path. If it was an odd two-join, I'll add an odd path. And then I do the same for the 2 part. I take A2, B2, C2, and I'll add a path that remembers whether the two-join was even or odd. And so we're going to tighten this up later. We're going to make this a little bit more precise later, but this is sort of the general idea of how you would take a two-join and decompose. And let me call these 2 parts the blocks of a two-join. So if I have a two-join, I'm going to decompose. I have a graph that admits a two-join. I'm going to decompose it into 2 blocks. Right? And these are the blocks. All right? And then if I have a homogeneous pair, again, I want to tell you how I'm going to decompose it. So in the two-join, the 2 blocks, the 2 parts were symmetric. Now the 2 parts are not going to be symmetric. So one part will be just A and B, right? A and B and the graph between them. And the other part is going to be all of this stuff, plus I'll remember A and B. I'll put a vertex that remembers A and a vertex that remembers B. And then what do I put between them? Do I put an edge or do I put a non-edge? So there's no good answer to that in this context, because with two-join somehow it was clear what I need to remember. I throw away the bottom, all I need to remember is the parity of the path. Here, between A and B, there's some general graph, so I don't know if I should remember an edge or a non-edge. So we'll come back to that later. But that's generally how you would decompose if you had a homogeneous pair, where here you would sort of see what you can do. Okay, so let's keep going. So I have the structure theorem. What I'd like to do is use it to color, right? You color the basic graphs, and then you take your graph, you break it apart into blocks, you color the blocks, you put them together. So skew partitions are bad for this kind of idea. It's not clear even how to break the graph into blocks. Forget how to put the blocks together. So what if I say no balanced skew partitions? What if I just want to look at perfect graphs that don't have balanced skew partitions? So then it turns out things get better. And so that's our main theorem, that there is a polynomial time algorithm that if I have a perfect graph with no balanced skew partition, so somewhere here it should say perfect, but so I give you a perfect graph with no balanced Skew partition, then I can get a polynomial time algorithm to compute weighted max click. So again, I give you a perfect graph, weights and vertices, no balanced Skew partition. There's a polynomial time algorithm to compute the maximum weighted click. Now, so that's the theorem. That's what I want to talk about. Now let's see why this is good for us, at least why it justifies the title. So first of all, not having a balanced Skew partition is something invariant undertaking complements, right? So Skew partitions you saw are invariant undertaking complements, and balanced, I promised you, is invariant undertaking complements. So then, if I can do this, I can also calculate weighted alpha. I can also calculate weighted stability number. And that implies I can color by theorems that I showed you some time ago. All right, so
in the decomposition, you require in each step, you don't have a balance.
Right. So that's a tricky bit. But I'll talk about it in a minute.
But alpha v just numbers. You cannot find the independent, can you?
So actually, if you can compute it, you can by sort of you delete the vertex and you see if the stability number went down. But you can do something, yeah. But at least to color, it's enough to just find the number. You don't need to find the actual click number or the actual stability, the actual click or the actual stable set. Okay. So, all right. So from now on, I'll be talking about this. So what's the idea? Okay. So remember the structure theorem. So now it got simpler because I don't have balanced Skew partitions. We say you don't need homogeneous pairs. So then if I start with a graph, so maybe it's basic, but then there are known algorithms to calculate more or less everything you want. So then the idea is let's continue decomposing by two joins. And let's kind of build a decomposition tree where every time I decompose by two joins. But as Sangil pointed out, there are two problems with it. Let me tell you the second one first. So the first problem is the second problem is I decompose my graph and now suddenly I introduce a balanced Skew partition. So now I don't know anything about it. The first problem is that you can't really afford such a big decomposition tree. You cannot afford a full binary tree. There are too many calculations you need to do. All right, if you want the polynomial time algorithm. So we'll take this idea, but we'll refine it so that it works. All right, so the first solution is something that Kristina Vushkovic and Nicolas Trotnion came up with in their previous work. So what they say was, let's try and get what they call extreme decompositions. What that means is a decomposition where at least one block is basic. So that's sort of right. So if I could always decompose by extreme decompositions, my decomposition tree would look like that, right? So I start with the graph, I decompose it. This is a basic block. I never touch it again. This is a complicated block, so I continue decomposing, and so on and so forth. And so, all right, that's one idea. Let's look for these extreme decompositions, and then the second idea is so that's to solve this problem, right? That's to simplify the decomposition tree. To do this, to get rid of balanced Skew partitions, we do something a little bit more general. So for that, we use what's called trigraphs. So let me tell you about trigraphs, because trigraphs are a good thing if you work with induced subgraphs. They were introduced for something, and then suddenly they were useful for something else, and then suddenly they were useful for something else, and anyway, somehow they make it easier to think about certain things. So what's a trigraph? You know what a graph is? It has. If I give you a vertex pair, maybe it's an edge, maybe it's a non-edge. In a trigraph, there are three possibilities. If I give you a vertex pair, maybe it's an edge, maybe it's a non-edge, or maybe it's an undecided pair. Right? So far it's just kind of an abstract object where you have vertices and you have three kinds of vertex pairs. And the undecided pairs I'm going to call switchable edges. And sometimes, no doubt, I'll call them wiggly edges because that's how we draw them. All right, so again, same thing said one more time. If you have a trigraph, so a trigraph has a set of vertices, set of edges, set of non-edges, set of switchable edges. These three sets are pairwise disjoint, and every vertex pair is in at least one of them. Okay. So let me give you an example. So now, okay, so what's the connection between, actually, let me go one step back. What's the connection between graphs and trigraphs? Well, if this set is empty, if there are no undecided pairs, then it's a graph. And then I can also say, here's a trigraph. Let's decide some undecided pairs, right? So from the name, you probably understand the idea. These undecided pairs, sometimes I'll want to think of them as edges, sometimes I'll want to think of them as non-edges. So let me say a realization of a trigraph is one particular assignment of values, one particular decision on this undecided pairs. So let me give you an example. Right, so here again it's written formally, but let me give you an example. So here's a trigraph. So edges that are like that, edges that are wavy, edges that are wiggly, they're the undecided edges. So for example, in this trigraph, 1, 3, and 1, 4 are the undecided pairs. 1, 2, 2, 3, and 3, 4 are edges, and every other pair is a non-edge. So I start with this trigraph. These are its possible realizations. Right, so this is a realization where I decided that all the undecided pairs are non-edges. This is a realization where I decided that both my undecided pairs are edges, and these are in between. All right. So now, if you've never seen trigraphs, the easiest way to think about them is to sort of think of properties of realizations. This is a bad way to think about trigraphs, but that's how we're going to do it here because most of you have never seen trigraphs. So let's see. So let me say that the trigraph is perfect if every realization of it is perfect. Again, I really will use a kind of different definition that doesn't use realizations, but this is something that everybody understands. However, I decide on the undecided edges, what I get is a perfect graph. Okay. So and then let me just tell you two definitions about trigraphs that I'll need. So first of all, I want to think about complements of trigraphs. And that's what you think. So I switch edges and non-edges, and something that was undecided remains undecided, right? So the same vertex set, the edges of the complement are the non-edges of the trigraph I started with. The non-edges of the complement are the edges of the trigraph I started with, and the undecided pairs remain the same. So then realizations of T correspond to complements of realizations of the complement of T, I hope. Okay, and then another notion that's not at all standard but convenient for me here, let me talk about the degree in a trigraph. So that's how many pairs that could be edges a given vertex is in, right? So the degree of V, it's the number of vertices U, so that UV is either an edge or an undecided pair. Okay, and then I'll remind this when we use them. All right, so one more step. So far these trigraphs are kind of pretty wild, right? So you have all these undecided edges leaving everywhere. Usually for most problems it's enough to kind of restrict the undecided pairs a lot. In fact, until now I think the only trigraphs that were ever useful to anybody are trigraphs where the undecided pairs are just kind of isolated edges, where the graph of undecided pairs is just a matching. So here we need to do something a little more complicated, and but only just a little bit. So let me say that the trigraph is tame if, so basically what I'm going to tell you is that the graph of undecided pairs is very simple. It's very simple. So the components of the graph of undecided pairs, they're either single edges or two-edge paths. That's it. And there are more restrictions on the components that's a two-edge path. So suppose I have some vertex which is in the middle of a two-edge path in the graph of undecided pairs, then either it has degree 2 in the whole trigraph. So these are the only possible edges or undecided pairs incident with it, and these two guys are non-adjacent, or the same in the complement. So this guy, he's adjacent to everybody. He's undecided about these two, and he's adjacent to everybody else, and these two are adjacent. So again, the point is, I call the trigraph tame if the undecided edges are restricted significantly. Okay, so then the good thing about it is you can prove theorems about them. So here's a tame perfect trigraph, right? So it's a trigraph, every realization of which is perfect, and the undecided pairs are restricted. Then either it's basic, which means, so the same thing as for graphs, except you need to define the classes a little bit more carefully, but you can. But the point is, so either it's somehow very simple, or it admits a balanced Skew partition, or a two-join, or a two-join in the complement, or a homogeneous pair. Now, you don't know what any of that means for trigraphs, but you do know what it means for graphs. Now it's easy to explain what it means for trigraphs. Let me just go back. So, here we go. So basically, the idea is, if I say a trigraph admits a decomposition, then I'm not allowing the edges that are important for this decomposition to be undecided. So for example, in a Skew partition, right, so what are the important edges in a Skew partition? It's important that everybody C is non-adjacent to everybody in D, and it's important that everybody in A is adjacent to everybody in B. So I'll say every pair with one end in C and one end in D is a decided non-edge, is a non-edge. Every pair with one end in A and one end in B is a decided edge, right, is an edge. But there may be some undecided pairs living somewhere, they're just not anywhere I care. Similarly for two joins. So all pairs like these are edges, all pairs like these are edges. All other pairs with one end in the top, one end in the bottom are non-edges, and I'm allowing non-adjacent pairs to live inside the top or to live in, I'm allowing undecided pairs to live inside the top or to live inside the bottom. All right? And last step for homogeneous pairs, so same principle. The edges, let me do it here because here I can reach. So these are edges, these are edges, these are edges, these are non-edges, these are non-edges, and everything else may be undecided. Okay, so here we go. One more. So that's the theorem, right? Either you're basic or it admits a balanced Skew partition in the trigraph sense, or a two-join or a two-join in the complement, or a homogeneous pair. And again, actually, you don't need homogeneous pairs. All right. So that's one theorem. Now let's strengthen it. Right. So here we said this is not needed. All right. So this is not needed, and you may admit a balanced Skew partition. So now let's strengthen it. So again, T is a tame perfect trigraph. Then actually you can do a little bit better. You can so maybe you're basic, maybe you admit a balanced Skew partition. And otherwise, you admit an extreme two-join or an extreme two-join in the complement, or you admit an extreme homogeneous pair. And just to remind you, what extreme means is that one of the blocks is basic. So I'll say it again in a minute. Actually, I'll say it here in a minute. Maybe. Okay, so let me go back. So first of all, this outcome came back, right? I kept saying this is not needed, but now if I want extreme decompositions, if I want decompositions that promise me this nicer decomposition tree, then I do need to bring this back. And I'll tell you in a minute how. So now also let me tell you again how I actually decompose, what the blocks of the decompositions are. And that's where the whole trigraph business comes in. So here we go. So suppose I have a two-join. Then the blocks are going to look like that. Where what does this mean now? So, right, so I have my top and bottom. And so, for example, the block that corresponds to the bottom, this is C2, by the way. So I keep A2 and B2 and C2. And then I add, a vertex that remembers A1. A vertex that remembers A1, a vertex that remembers B1. And then I add an undecided pair between them. Right? So then I say they're an undecided pair. So I no longer add a path where I need to sort of decide how long the path is and it interferes with all sorts of things. All I add is an undecided edge between them. So that's in the case of an odd two-join. In the case of an even two-join, it's almost the same thing, except what I'm going to add is a path of length 2, right? Where both edges of the path are undecided. And this guy is not adjacent to anybody else. So that you see where, right, if I start with a graph and I decompose like that, I keep adding undecided pairs, but they're under control. Either I add just an edge, or I add so far a two-edge path where the middle has length 2. Okay, so then you do the same thing in the complement. So don't look too closely at these pictures, but that's just to show this is the other case when I add a two-edge path and the middle vertex is complete to everything. But it doesn't matter. may not dwell on these pictures. And then finally, I had finally, how do I decompose a skew partition? I'm sorry, how do I decompose if I have a homogeneous pair? Well, remember we said one block is going to be A and B, the other block is going to be this, but I don't know what to put between these two vertices. Well, now I do put an undecided edge, right? That's exactly how trigraphs came about. How do you decompose a graph that admits a homogeneous pair? Now, for two joins, we said decomposition is extreme if one of the blocks was basic. For homogeneous pairs, the blocks are not symmetric, so I'll say the decomposition is extreme if this is basic, if the top block is basic. All right, so now you know what the theorem says. All right. So the next theorem answers your question. So if I decompose like that, if I decompose the way I told you, then the decomposition does not introduce a balanced skew partition. I decompose the two graphs I get don't admit balanced skew partitions again, or at least the one that's not basic doesn't. Okay, so now we get the theorems that we wanted. I start with the same perfect trigraph with no balanced skew partition. And then I can decompose it all the way down to basic trigraphs by extreme two joins in the complement, or extreme homogeneous pairs. So the reason I can go all the way down is because we said the blocks don't admit balanced skew partitions either. And actually, it turns out the idea for choosing this decomposition extreme is really easy. All you do is choose a decomposition where one side is minimal. So if you see that your trigraph admits a two join, then let's choose a two join where one side is minimal. And you're guaranteed, well, you can prove that that side is going to be basic. If you see a trigraph that admits a skew partition, a homogeneous pair, then you want to choose this minimal, right? The kind of the block that's going to be basic. So almost true. Sometimes I need to switch. So here's a trigraph. I saw it admits a one join. Now I'm trying for an extreme one join by making one side minimal. And then I see that actually I can find a homogeneous pair where this is even smaller. So then switch. So it kind of guides you into the correct decomposition. And that's why we needed to bring homogeneous pairs back. It's not true, right? If I didn't say that, then this doesn't work. But as it is, it works. Okay. So now we're basically happy, right? Now we get a decomposition tree which is small. So there's just a couple of things left. So here's the decomposition tree. Maybe it's not so small from where you're sitting, but it doesn't branch too much. So I start with the graph. At every node of the decomposition, one side is basic, and then I keep going. Right? So this guy is basic because I stopped at him, and all those guys, all the G2i's, are basic because that's how I designed my decomposition. And what's important is that all of these guys become smaller. Okay? Actually, it's not even that important now that I think about it. Forget about that. Okay, so now the point is, so now we're finally ready to do what we set out to do. We're going to compute the weighted clique. So I have a trigraph with weights on the vertices, and now actually what I'm going to compute is what's called a strong clique. What that means is, so a strong clique in a trigraph is a set of vertices that are all pairwise adjacent, right? I'm not allowing undecided pairs. It's a set of vertices, and every pair is a decided edge. Now, if you start with a graph, then a strong clique and a clique, well, then the strong clique is exactly the same as a clique, right? Because there are no undecided pairs. And what we're actually going to compute is the maximum weight of a strong clique in a trigraph. And again, if what you're really interested in is graphs, then that will give you what you wanted. Okay, so how do we do it? And I'll show you, right, so we have 5 different kinds of decompositions. Even two joins, odd two joins, even two joins in the complement, odd two joins in the complement, and homogeneous pairs. I'll just show you how to deal with two joins, with odd two joins, but all the rest is sort of the same but a little different. So here I am, I have a trigraph T. Right, so what I'm going to show you now is how, if I have a decomposition, how I can reduce the problem of solving max weighted strong clique here to the problem of solving max weighted strong clique in the two blocks. So here I am. I have my trigraph T. I decompose it into two parts, T1 and T2, and then T2 is basic, G2 equals T2. So now what you're going to do is the following. So in a basic graph, you can compute anything you want, right? You have time to compute anything you want. So I'm going to compute the max weighted clique here. It's going to be called A. The max weighted clique there, that's going to be called B. And the max weighted clique of everything, that's going to be called C. And now I'm going to change the top. So currently the top looks like that. And let me call this thing a marker for the top, right? So I took my top block and then I marked the fact that it came from a two-join by this undecided pair. So then I'll take this marker, I'll take this undecided edge, and I'll replace it by what I call a gadget. And what a gadget is a vertex complete to A1 and anti-complete to B1 with weight A, a vertex complete to this and anti-complete to that with weight B, and a vertex anti-complete to everything with weight C. And now I claim that in order to compute the max weighted clique in T, it's enough to compute the max weighted clique here. All right? So, okay, so far it just shows you how to deal with one decomposition. Now let's see how to do it in the whole graph. So here I am again. This is my tree. So what happens? I start with a trigraph. I decompose it once. I have a basic block, and I have another block that's not necessarily basic, but it has a marker undecided edge. It has an edge that came from the decomposition. Then I decompose again. So I have a basic block, and I have a block where now I added another marker. Right? Every time I decompose, I add a marker. Now I decompose again. I have a basic block and a block with another marker. And I keep going. So now when do I stop? I stop when this side is also basic. So now what it is just a basic graph with a basic trigraph with a bunch of markers. And the markers don't interfere with each other. That's because, well, that's how the decompositions work, right? An undecided edge is never an important part of the decomposition. So then what you do is, for every marker, you replace it by a gadget. I showed you how to make a gadget for odd two joints, but you can make a gadget for everything. Now the trick is, so there are two important things now. So this is basic. The gadgets are designed carefully so that when I replace the markers by corresponding gadgets, what I get is another basic trigraph. And also, because of the argument, because of what I showed you on the previous slide, this is true. To compute the clique in the original graph, all I need is to compute the max weighted clique here, where the markers are replaced by gadgets. And so I can do that because this is now a basic graph. And so we're done. Thank you.